Çok da zaman. Evet, bu arada yine ilk webinarımızdaki gibi bu sefer de yine kayıt alarak sonrasında YouTube kanalımızda yayınlıyor olacağız bu webinarımızı. Öncelikle geldiğiniz için teşekkür ederiz. Bugünkü konuğumuz Dr. Theo Vinceslas. Kendisiyle Matthieu Pedergnana moderatör olarak bu webinarı yürütecek. Soru ve cevapları alacak. Kendisinin bir sunumu olacak. Burada da yazdığı gibi Hafif Kerpiç konumuz. Theo'nun araştırmalarından kısaca Matthieu size bahsediyor olacak. Sunum ve devamında İngilizce olarak devam edeceğiz. Umuyoruz ki imkanlarımız el verirse tüm bu sunumları, bu bir webinar serisi bu arada, Haziran sonuna kadar devam edecek. Yaklaşık 7 tane webinarımız olacak. Bu ikincisi. Her birinin Türkçe altyazı koymayı umuyoruz. Dediğim gibi şu an için İngilizce olarak bugün devam edecek webinarımız. Ben sözü Matthieu Pedergnana'ya bırakıyorum.
Matthieu.
Evet, buradayım. Merhaba, teşekkür ederim herkes için, burada olmak için. Şimdi İngilizce olarak devam edeceğim. Thanks a lot for everyone to be here today. I'm really happy that we could have Theo Vinceslas for this seminar tonight. Theo is an engineer and a doctor in engineering, and he has been working for this PhD thesis on light earth and how to find the best combination of hemp and earth to create a good insulation material. And he is now working at the Architecture School of Normandy in Rouen and trying to establish research over there on this topic. He will today speak with us about this very interesting topic that some of you know that I have been supported since years, how to create light earth material and what are the performances, what materials can be used for it, and especially local materials. So thanks a lot again, Theo, for being here and sharing your knowledge with us.
Thank you. Thanks a lot for the presentation. So may I start the presentation?
Yes, please.
Okay. So yeah, thanks again for welcoming me, and I'm really happy to participate for the association events. So I'm going to read directly. So I'm gonna speak about firstly of a little definition of what is light earth, and then I'm gonna try to show you how can we formulate, so what are the possibility of composition of earth and hemp and other vegetal fibers that we can use for light earth. Then we're gonna speak about exactly the formulation. So how do you make the quantities? How do you calculate the quantities of earth and vegetal particles? And finally, I'm gonna show you the influences of composition and formulation on the performances sorry. And finally, at the end, we're gonna see some examples of mixing and implementations, and we will maybe have the time to discuss the advantages of this kind of material in seismic zones. So if you have any questions, please don't hesitate to ask it, and I can stop the presentation anywhere and we can have a discussion. I think it's better like this when we have like some interaction. So yeah, please ask question if you have. So yeah. So we begin. What is light earth? How can we make the definition? So it's really simple. It's actually, we can call it a low technology because it's just earth that is mixed with water to make an earth slip. And besides, we have vegetal aggregates. So here it's an example of hemp sheave, and then we mix it, and we have different kind of implementation. So I'm beginning here the presentation with simple example, and then we're gonna go with more specific examples at the end of the presentation. So firstly here we have an implementation between formworks. So it's actually between an existing wall and a formwork, a wooden formwork. So the mix is actually poured between the formworks. We can spray it also with a machine, a specific machine made for lime hemp or other kind of sprayed materials. And we can also make some prefabrication, so make some bricks by molding or by spraying also. So this is really the simple definition, and maybe to go a little deeper in the definition, we can look at the densities. So what is it? Why is it called light earth? Actually, it's because of the volumetric mass or the density that is quite low to make it like an insulating material. So here, what you see is different example of raw earth with fibers or with vegetal aggregates and their corresponding densities. So when we take raw earth or soil like completely, it's between 1,600 or 1,800 kilogram per meter cube. And when we add some fibers to it, like maybe you have some example in Turkey of wattle daub. So we add just like some wheat fibers to the earth and lighten it a little. So it makes something like 1,200 kilogram per meter cube. And then you have like the first kind of example of light earth, but applied with a trowel. So it's quite dense, actually. It's still quite heavy. It's around 900 kilogram per meter cube. And then we begin to really talk about light earth. So between 200 and 500 kilogram per meter cube. So this is, yeah, maybe the precise definition of light earth is by its density also. So we have the composition and the density, and as I said before, you can do it between formworks, and you can spray it, and it's actually I put here the same densities, but it's actually a little bit different, and we're gonna see it through the presentation. And finally, at the end, you can do also what we call stabilized aggregates. It's actually just vegetal aggregates with a very, very little amount of earth slip, but it's not something that can be put without some formwork. So you have like still formworks that have to stay. Okay. So yeah, I did a thesis on light earth, and I studied particularly the variabilities and the influences of the variabilities on the performances. So I'm going to speak actually quite a lot about variabilities, but the idea is precisely to know this variability and to be able to work with it. Not really to search for the best combination or the best material, but to be able to, each time you have a material under your feet or behind, you can work with it. So you have to know how to look at the variability, and then know how to work with it to be able to do some light earth that have good performances. Okay, so for the earth, we can look at different type of characteristics. We have the particle size distribution or granulometry. You have the clay type, sorry, and something that is actually characteristic of the clay type is it's the clay's activity. And then beside you have the vegetal particles. Here is hemp, so it's an example. And same, you can look at particle size distribution. You can look at dust ratio or bulk density. So it's here a first look at the characteristics of variabilities. So what I did in France is that I went through the west of France, the northwest of France, and I collected a lot of different kind of soils. So here's a map of what I would have been collected, and I collected from private properties and also from quarries. And I had from quarries, I had like sludge with or without flocculants. I had like final products in bags or raw material before sieving. And with all that, I did different kind of characterization. So here's the first one. It's called a Carrasas test. So what is the Carrasas method is that you put all your different kind of earth and with different kind of, different type of water content. So here vertically, you can read actually 25, no, sorry, it's 15, 30, 45, and 60% of water contents. And what we see is that we have different kind of behavior as a function of the water content. So it's actually a really simple way to know how the earth gonna behave with the water, and it's actually saying a lot of its composition. So we're gonna look at it a little bit. So it's actually a little bit more than just water content. We can also look at the compaction energy. So sorry for the picture in French. Some of the pictures gonna be in French. I didn't have the time to traduce all of it, but still. So this one actually show the making process of the Carrasas test, and you have like vertically different kind of compaction energy, and horizontally you have different kind of water content. Different water contents. So by doing this, you have here for one earth, different way to see how it behaves. But for light earth, what we look at and what we need to look at is really the behavior with the water. And then obviously you can do it with different kind of earth. So if we look a little more precisely here on the different kind of earth, we see that we have different kind of behavior in the function of the water content. And actually with the water, if we read the water content lines, we can see that for one earth, we're gonna have like total segregation or a cylinder that stands. So actually this gives you an estimation of the particle size distribution, and we can actually say quite easily that the more you have fine particles, so like clay or silts, the more you're gonna have absorption of the water, and the more you're gonna have like a standing cylinder, even with a lot of water inside the earth. So actually here, I don't know if you see the mouse, but we can say, for example, that this red earth, the earth that is really red, have a lot of clay, and just the one that is at the, I mean, the two that are near have really less, really less clay content and really less like fine particles. But so this is not really, I mean, we cannot say that it's a scientific method. It's really like something that is made to observe the behavior, and that is something that can be made also to learn how to look at the earth, and or also on sites, on building sites, when you need to choose between different kind of earth. But if we look at this more precisely in the scientific way, so here is a representation of this particle size distribution. It's actually in the blue triangle all the earths that have been collected that I show you before the map, and the green dots are the natural variability that we can find in Normandy or in Brittany in France. Okay, so this is to show that the study that have been made on light Earth have been based on the maximum of variability that we can have naturally. So to say, actually, the goal, I mean, the aim was to be able to conclude on are we, on the question, the following question, are we able to build with lighters and with any kind of earth, or do we have to look at a precise type of earth? So as I said before, there is a lot of different kind of characteristics that can be looked at in laboratory. I'm not gonna spend a lot of time here because I don't think it's the goal, but it's just to show you that there is not just the particle size distribution. There is also like the density of the earth, and the characteristic of the clay. Okay, so I showed like what have been made in France, and you can say for obviously what about the Turkish soils? I wanted to say that there is an example that I use a lot actually in my classes when I talk about earth materials and earth buildings. This is actually the first example that I speak about when I'm in front of the students. I show them this site of Çatalhöyük. I don't know if I pronounce it well, but still, so it's good. Okay. Thanks. So yeah, so we can find their mud bricks, and it's actually the kind of the oldest example that we have nearby Europe and Asia. So there is a lot of example like this that shows that you have everywhere a way to build a way to build with earth. And actually we're gonna see it, but I mean, there's a really big variability of earth, and a big amount of this variability is usable for light earth. Light earth is actually really, I mean, not really, I don't know how to say, but we don't need a precise earth, and I'm gonna show it to you. So yeah, so I found actually just a little scientific article that shows the viability of earth that you can find in Çatalhöyük, and you can actually see that even there's already a big variability, and even with this variability, they have been able to build with mud bricks. So this is to say that even in ancient times, even with a big variability, we have been able to build. So now how you can test if you can build with light earth. This is the first example of test that you can do. You can so mix earth with water and try to do this test. So it's the hand glove test. So the objective is to have the hand on the middle. When you have the hand on the left, it's like you have too much earth on your earth slip, and when you have the hand on the right, you have not enough earth inside your earth slip. But it's actually also a way to make a characterization of the earth you have, because if you're not able to have the hand in the middle, the glove, the real glove, it says that actually you cannot build with light earth. I mean, you cannot do light earth with the earth. Okay. I'm not sure if I'm clear enough, but yeah. Okay. So actually during the thesis, we tried to develop other kind of tests that are more quantitative, that we can actually measure something. So we
it's okay. I just muted.
Okay. So yeah, I was saying that we developed some tests. So here they are. There was there were the spreading, the immersion test, and the rough wall cone. So the idea was actually everywhere to measure rheological behavior. So how the earth slip was flowing actually, and every time we managed to find a way to measure and to quantify the behavior that we see actually when we do the glove tests. So each of these tests are usable on site to characterize also the earth slip. But the thing is that we don't have the right way, to say that they are equally valuable. The thing is that we still have to say for each earth what is the measure that have to be reached. So that's why I say it's still tests in development. Okay. So we saw the variability for earth, and now we're gonna see the same thing for vegetal aggregates. So actually, when we look at hemp, so you have a picture on the right of a hemp stalk, and on the outside, the bark is used to make a wool, so hemp wool, and the interior is like a kind of wood, and so we call it when it's crumbled, we call it sheaf, so hemp sheaf. And so for this material, here is a representation of the microstructure of a hemp stalk, and the outside, what is red, the same thing, you see the wool, the bark, and on the inside the wood that make the sheaf. And what we see is that this is highly porous, so it makes a lightweight material. It encloses the air, and so what we know is that low thermal conductivity is directly linked with insulating properties, and so with low densities. So I put just a little graph here to say this actually. So I put on this graph all the dots are all kind of building materials that we can have. So when you go on the far right, you have materials with high densities like concrete, like fired clay bricks, and so they are not insulating materials because they are dense. So we can see it on on the vertical axis. And so actually all the thermal insulating materials are on the far left, and behind, I mean, under 0.1 of thermal conductivity. Okay. So yeah, so this is to say that the heat conduction property is directly linked, directly related to density. So this is actually the aim when we do light Earth, is to try to reach the lowest density possible. And so why we use vegetal aggregates for this is because their structure allows to optimize the density, and because of their structure, we can reach some very low densities of light Earth. So actually, the example here is for hemp, but this kind of structure is often found in vegetal particles. So actually, you can find same kind of structure in other kind of particles that maybe you have more in Turkey. So that's why I did some research to find this. So this is actually a paper, like a scientific article from colleagues that tried to analyze, I mean, characterize the different kind of plant aggregates, plant particles. So in A, you have flax sheaf, then hemp sheaf that we saw just before. You have maize bark, you have miscanthus, reed, rice husk, sunflower bark, sunflower pit, and wheat. So what we say here actually is that with all these kind of particles, you can also make light Earth, because you have the same kind of microstructure inside the plant particles. So you're gonna be able to reach also very low densities and try to make insulating materials. So maybe this table is a little too much, but still, this is in the same articles and and so we see here the densities of the different kind of vegetal particles that varied between 20 for the sunflower pit and 130 for the miscanthus. So yeah, the hemp sheaf that have been really studied is actually around 110. So that says that if you have like a lot of sunflower, for example, or wheat, you can even do higher performances that I'm gonna show you. Okay, so there is actually the characteristic of density, but there is also, I mean, we have to look at the particle size distribution, sorry. So this is again in French, but we see that there's zones in red that shows approximately the particle size that can be used in light Earth. So this is actually between few centimeters, like 3, 4, 5 max, maybe, and few millimeters. We cannot use fibers like the wool of hemp that is here, because it's too hard to mix. It could be mixed manually, but like every time you try to mechanize it, it's too hard to mix earth. I mean, like earth slip and fibers. I mean, long fibers. So you have to use particles and between like few centimeters and few millimeters. Okay, so how actually you do the mixing? So firstly, you mix raw earth and water with a paddle mixer, for example. So here is an example of a really simple way to do it. So it can be used on little building sites like little homes. So after you did the mixing, you sieve it with a 2 millimeter sieve to remove all the big particles and to keep just the fine particles that are going to be used for the bonding of the vegetal particles. Then when you have your earth slip, you correct the water content. So if you have too much earth and you see it with the hand glove test or with other tests, you can add water, or if you have too much water, then you can try to make another slip and mix them together to be able to find again the good glove. And then you'll be able to mix slip with hemp, also with a paddle mixer, for example, or I'm going to show you at the end how it can be mixed in other ways. So actually, as I said, this is a really simple test that is still used in France by the craftsmen. But yeah, the water content can be an influence on the mechanical behavior and on the thermal conductivity or density. So we saw that the aim is to reach as lowest as possible density, but you have to keep a good mechanical behavior. So actually the glove test has made a real good experimentation for the craftsmen, and we still say that it allows us to be able to reach good performances in terms of mechanics as in terms of thermal conductivity. So the study that I made was on the lot of different kind of formulations. So actually I studied different kind of earth, different amounts of hemp, different kind of hemp also. You see different particle size here. I tried also to add some sand to see the influence at the beginning of the type of earth. And here you have different type of earth that have been used with the same formulation, so the same amount of earth, water, and hemp. So this was to show you the really, I mean, in the graphic way, the examples, and after we're gonna see some figures on the performances. So yeah, the aim is still to reach a really low density. And so actually here are some results of the study. So on the left, you can see all the formulations that have been studied in terms of densities on the horizontal axis and in terms of thermal conductivity on the vertical axis. So what we see is that we have kind of important variability with all the different kind of earth and all the different kind of formulation that have been studied. So we vary between 0.06 and 0.12. But if we look at the right, then on the other graph, I compare actually all these points that are resumed by the 2 points, the two big blue points, and I'm comparing this with other kind of materials. So this is still in French, sorry, but in red cross you can see other kind of light earth that have been made with other kind of aggregates, like the one we saw before. We can see here it's wood cellulose or paper cellulose. Here you have like other kind of materials, insulating materials like lime hemp here, and yeah. So what we see is that the viability that have been found with all the earths and all the different kind of hemp that have been used is still in the range of the viabilities that of the materials that we found on the markets. So actually, everywhere you are and everywhere you try to build, you'll be able to reach performances in this range. And actually, when you are under 0.1 in terms of thermal conductivity, you're already kind of good. So this is to say that you'll always be able to find a way to do a good light earth. I mean, a performance, a good performance with light earth. So, sorry. Okay. So this was in terms of thermal conductivity, but there is also aims in terms of mechanical performances. And what we say here is that we see the mechanical performance in terms of compression, and with the different kind of earth that have been used, we are between 0.15 and 0.2 megapascal. So maybe this doesn't really speak to you, but the thing is that to be able to have a material that is self load bearing, so this is not a material to bear any other kind of load that just maybe the render. We just need to be able to self load bear the material. So this is to say that is actually really enough. If you reach actually 0.15 megapascal, you'll be able to do more than 4-5 meters of light earth without any kind of structure. And yeah, the other thing that is said in this graph is that obviously the more clay you have in your earth, the more compression resistant you're gonna be able to have. But even if you are with the lowest amount of clay, so it's actually around 10% is here because it's in volume, but if we look at in mass, it's actually around 10%. So actually the minimum that you have to reach for your earth is around 10% to be able to use it for light earth. So yeah, obviously if you have something like fully sand or really low amount of silt, then you cannot use it for light earth. But most of the time you will be able to find an earth with a quite good amount of fine particles, and then the clay fraction could easily be around 10% or more. Okay, so we have different kind of mixing. So here the first one is really, is a one that is used with a machine. So firstly we mix the earth with water, like the day or 2 days before, so that the water will be able to reach all the parts of the microstructure of the earth and make a good dissolution. Then we sieve it, as we saw before, and then the slip is after correction put in the machine here that just continuously mix the earth slip and send it with a pump here to the sprayer. So actually, the sprayer that you see here is made that you the following way. You have like two outs that gonna spray just the mix of earth and water, and another big one that send just the hemp sheave, and the mix is actually made on the wall. And so the other way to do it is obviously to make it with a I don't remember the name in English, but yeah, concrete mixer. Thank you. So there is here an example of concrete mixer. So you can also make the light earth mix with it, or you can also make it with a planetary mixer. Actually, it's also a quite good way to do it. The planetary mixer works really well. Okay, so what are the different kind of implementations that you can do? It's actually if you know already hemp concrete or lime hemp, we can do actually everything that is made with lime hemp. We can do it with earth hemp. So it's mainly thermal insulation of walls. So on the top you have like examples of it's cut designs, and so on the top you have like examples of new and wooden structure that we're gonna fill with light earth. So it can be between formworks or sprayed with one formwork from one side. And on the bottom you have like examples of renovation when we want to double an existing wall. So on the right, on the left, sorry, when it's written A, you are not. I mean, you can do it without a wooden structure. You can spray it directly on the wall, but it have to stay less than 6 centimeters. So yeah, under 6 centimeters of thickness. If you want to go further, more than 6-7 centimeters, then you have to add a little wooden structure. So it's like really little section. Is like maybe 4 or 5 centimeters of sections, and it's gonna be used to maintain the mix during its fresh state. So here is all examples of insulating walls, but you can actually also do slabs, or you can also use the light earth to insulate roofs. So yeah, this is again to say again the process of doing the light earth. So yeah, the earth slip preparation, you have earth and water mixing, then sieving, then the cohesion test with the glove or with the other tests, then you validate or you modify your slip, and then you can implement by firstly preparation of the site. So if you double a wall, you're gonna have to wet the wall a little, for example, or you're gonna have to prepare your formworks. Then you can spray in several passes or pour the melange, the mix, sorry, in the formworks. And then if you spray, you're gonna have to do a little rectification of the surface to be able to have something that is totally like homogeneous. Okay, so I present here some examples of insulation. So yeah, on the top right, this is a thermal insulation, but by the outside, by spraying. So it's actually lime hemp, but we can do the same with earth. So you have a formwork on the inside, and it's a wooden structure, and we're gonna fill it with earth hemp. On the bottom, you have like example of prefabrication of bricks, and then we do masonry, classic masonry. So you can actually also do some reparation. You can double existing walls. You can insulate by the outside with bricks or from the inside. And actually, this is a really, I mean, for me, it's kind of the better way to renovate this kind of walls. I mean, when you have like traditional walls with stones, you have to keep the perspiration. I mean, the transportation of the humidity from the outside to the inside, and from the inside to the outside. And so actually, when you do earth hemp, you'll be able to keep capillarity between the inside and the outside, and so be able to make a good transportation of the humidity through the wall. So it's actually a really good way to maintain a good hygrothermal comfort without having a big ventilation. So as I said, you can also like do roof insulations. So here it's an example of a wooden structure that is filled by the outside. And it's actually, I mean, why it is interesting to do this, it's actually because you're gonna have a good inertia. You're gonna have like an insulating material that is a little bit heavier than classic mineral wool. And so for thermal comfort in summer, it's really interesting because the heat is gonna have a lot of time to pass through the roof and warm the inside of your house. So actually, when you have like this kind of materials in insulation for roofs, is really nice for a hot climate. So this is also a different kind of spraying. And then for the end of the presentation, I'm going to show you some examples. So here is a quite recent example of spraying in a wooden structure by the inside. So it's actually in Normandy in France. So we have a full wooden structure that have been filled from the inside on the walls and on the slabs. So this is the dry state. This is the construction process. So you have like the wooden structure that have been made. This is a renovation, and then the earth hemp have been rendered with lime on the outside. So this is during the construction process on the inside, the filling actually to help the spraying process. You can add a frame that we see on the wooden structure. It's gonna be useful to not to have the rectification to do, to have an homogeneous surface. So it's actually easier to spray through the frame that we see here. This is an example of filling a wooden structure from the outside. So it's also a renovation, and we have been doing a thermal insulation from the outside with the the earth from the garden actually. So this is also the making of an example. Okay, so we can also make some prefabrication of wooden structure and then fill it with earth hemp and then put it on the construction site. Sorry. So this is a big example of prefabrication of earth hemp. Actually, this example, so you see it's quite gray, but the earth was gray, and so the prefabrication was made in a site apart from the building site, and you can see that the formwork is made from reed. And so this is the construction after. The live render also. This is another example from the same craftsman. So this is Acta, and they made a factory and they sprayed actually earth hemp on mud bricks that you see behind. So it's actually how do we say? Yeah, compressed earth bricks. So CEB that we see behind, and then we have sprayed earth hemp on it. This is a private apartment in Paris. So you see different types of earth implementation. So you have actually ram earth, wattle and daub, and light earth on the top. This is also like apartments and little homes. So actually we don't see here the light earth, but it has been put under the render that we see on the right. So it's actually also a wooden structure filled by the inside by spraying light earth. So yeah, to end the presentation, I wanted to maybe just discuss some advantages to put light earth on seismic zone. So we have actually ongoing studies on the research program that is called PNTER for Projet National Terre. So it means national projects on earth construction. So you can actually find it on internet, and there are a lot of studies ongoing on different kind of earth building styles. But there is one study on light earth, and we try to look at the behavior in seismic zone. But what we actually do as a hypothesis already is that we have a high deformation capacity. So it's interesting because it's not gonna be like breaking easily. We have actually a gradually crumbling, and it does not break in a fragile way like concrete. So you're gonna not have like big amounts of light earth that can go down. And it's actually also a material that can participate in the bracing of structure. Okay, so I put like just some personal work by bibliography, but I can send some some references to Matthieu and he'll be able to reach to you. So thank you for your attention, and I hope we have some time to have a discussion.
Okay, thanks a lot, Theo, for this presentation. Very technical, but at least for me, very interesting because of all this technique behind and all those information that are necessary to be able to use those material properly. So thanks a lot for it. I do have a lot of questions. I have seen that in the chat there were some questions also at some point. So maybe we can start like this. People that have questions, you can directly open your microphone and ask your question, or if you're not confident enough with your English, you can just write it in the chat and I can also tell them to Theo. Yes, Merve, and I see that you're ready to speak.
Thank you very much. I have one question. Your mapping project, your research where you mapped the clays around France, it was mainly about, and you also told about their performance, but it was mainly for light earth or also for plastering. Did you check also their performance for plastering, or you only concentrated on light earth mix?
So it was actually only for light earth, but we had actually a process to collect this earth because we wanted to reach the extreme parts of the variability that we can have. So actually we asked all the craftsmen that we know to give us some earth that they used. And it was actually used for different kind of things. So most of the time, actually, it was used for plaster. Sometimes it was used for waterland dome. Sometimes it was used for cob. But most of the time, it was render also. But for them, it was earths that was quite hard to use because they had some extreme behavior. Could be because they had a lot of clay or not enough, or so we wanted to have this extreme behavior to be able to reach a large variability. But yeah, it was just for light earth.
Okay. Thank you.
Thanks a lot for this answer. And yes, I had also a question about this type of earth. So after testing all these different variabilities or these different type of earth, then at the end, can we really use any type of earth if there is a minimum of clay?
Yeah, actually, so we did we had two conclusions on this question. The first one is on the particle size distribution. We saw that, we had one formulation with one earth that was not really not usable because it was crumbling down even when you made it and after it was dry. It was with a soil that was too sandy. So when you have too much sand and not enough clay, so it was actually around here. When you have really a low amount of fine particles, so yeah, behind 10% or lowest than this, you cannot use it with light earth. But most of the time you can do it. And what we did secondly is that I didn't show this work, but I had a colleague who knows how to transfer all this data in terms of maps, and we tried to see if everywhere we are in Normandy and Brittany, are we able to find some earth that are, that are suitable for light earth, as we said before, like, so in terms of particle size distribution. And actually, we saw that everywhere in this territory, you always have like some kind of earth that are available in less than 3 kilometers around. So yeah, most of the time you can find, in this condition, but I think it's like mostly, usable data everywhere, and mostly, and yeah, maybe in Turkey.
Okay, thanks a lot. And the second question that is related to it, it's what about if there is too much clay? Don't you have any risk of shrinkage?
It's a good question. Yeah. So yeah, I had a earth that was really clayey, the tier 1 that you see here. It's actually hard to find. To have an earth that have more than 50 or 60% of clay, but maybe you can have one. And if it's the case, then you're gonna need to have a really low amount of earth for a good amount of water. And actually, the fact that you have a lot of really a lot of vegetal particles, it's making an armature. I don't know how to say, but
a skeleton.
A skeleton, yeah, that's it. So you have a skeleton, and it allows your materials to have a almost no shrinkage. The more that I saw was behind 2%. So yeah, it's actually really low. But it depends also of the way you implement it. If you spray it, most of the time you're gonna, you're not having any shrinkage. But if you do a pouring between formworks, then you have to add a little more water to put it, and sometimes you can have shrinkage, and most of the time when you have like more clayey earth here.
Okay, thanks a lot for it. Because in Turkey, at least in the condition we are working, we have clays that have easily 60%. Soil that have easily 60% of clay, red clay.
Okay.
That is really shrinking, and so knowing that using the spraying method can also reduce the shrinkage is really important. Using the spraying method. It was a question in the chat about the resistance to this material to fire.
Yeah. I thought about it by doing the presentation, and finally I forgot. I'm sorry, but I didn't have the results in English. I had like some articles in French, but we have some results on fire resistance. Sorry, and actually, there's also an ongoing study in the National Program of Research on Earth Material. What we see is that for most of the formulation that is used to insulate the buildings, we have a really important fire resistance. Sorry, I wanted to have, to check. Sorry, I'm just going through the presentation to go through some results. Here. Okay. So what I've been found is that when you are above 250 kilogram per meter cube, you have really no problem with fire resistance. Like we reach the higher class of material for French regulations, and it's really like not crumbling at all when you are above 400. But then when you are above 400, it's not interesting in terms of insulating material. But so the thing is that with French regulation, when you are above 250 kilogram per meter cube, you reach the good condition, and you are fire resistant. Why? Because actually you always have earth around your vegetal particles, and so you have a really low amount of vegetal particles that can take fire.
And this is just for the material, so without protecting it with any plaster.
Yeah, that's it. So when you add plaster, then no problem.
Okay. Thanks a lot. So yeah, this was a very interesting question, because there is always a risk of fire in such kind of buildings. So, I don't know. I think Anta Merve, do you still have a question again, or did you keep your hand?
No, I have a question.
Okay, please.
So thank you very much, Theo. My question is, you talked about the heat isolation performance and also the heat storage performance.
Yeah.
There's a good balance, because you said that they are not so light like the glass wool, rock wool, like these isolation materials. So in that case, we are talking about a material which also has a certain capacity of a heat storage capacity. And that's good for the hot climate regions. Now my question is, we have in Anatolia, I'm sure in France you also, hot climate zones, also on the shore side, on the seaside, and also in the land side. But the difference is, in the land side, we have the same high temperature in the day, during the day, but a rather low temperature during the night. So that gives us the chance to cool the building down. So do you have any tests or experiences between the difference? So how is it if we use it on the seaside? How is it if we use it on the land side because of the night temperature?
Yeah, this is a really cool question. Thank you. Actually, I think that the question goes further than just the light earth material. It's really in terms of strategy of insulation. I made recently a study for the Caribbean islands, and how to build with earth there. And actually, people there are insulating on only their roof, and they don't want to put too much insulation. So actually, I had this kind of discussion recently. So what I mean, for me, what I saw is that it's always better to have more insulation, because when you have actually a good heat storage and good inertia, then the heat wave will not go through your walls or your roof. So even if the night you have still hot temperature, the heat, I mean, there is still a little bit of difference between the day and the night, and even this little difference is sufficient to remove the going on of the heat wave through your roof or through your walls. So for me, yeah, I think it's I mean, yeah, it's a good way to insulate buildings. Either you are on the seaside or you are on the land side. The more you have this kind of material, the more nice comfort you're gonna have inside your building.
Thank you. Because in Turkey we have the situation that the only exception is maybe Thracia, the European part of Turkey, but the whole Anatolia, after a short seaside, suddenly the mountains go high, and then the karasal iklim, the land climate zone begins very close to the shore because of the mountains which start just after the shore, and that's in whole Anatolia the situation on the Mediterranean and also on the Black Sea. So only a few kilometers here make a very big difference.
Yeah, okay. Yeah, there is also a phenomenon that I didn't speak about because I thought it was maybe too long, but maybe I can show you if I find it again. I have some presentation about it. It's actually the way that you have like kind of natural climatization in earthen materials, because you have like the fact that the water can evaporate or can condensate inside your wall, because in earth walls or light earth walls, you always have a little amount of water. And this water is actually how do we call it? Is like I don't remember, but the thing is that, yeah, when you have the heat wave that goes through your wall and encounter the water, if this water is in a liquid state, it's gonna evaporate, and the evaporation consume energy. So it actually by the fact that you have water, the consumption of energy make a kind of natural climatization, because it reduce the heat wave that goes through your wall. So that's why actually it's really cool inside earth buildings in really hot climates, when you have like, when you are in the desert and you have like a really ancient earth building heritage, you're inside, and it's actually pretty cool because you have this phenomenon.
But this is for example, for light earth, the clay amount should be more than to have this.
Yeah, the more clay you have, then the more you have this phenomenon.
I mean, this is like for any type of construction, a choice between the density and the amount of insulation we want. It's unfortunately, as an architect, always what we have to think about. Okay, do I want more insulation or more thermal mass in my building? And yes, thanks to those studies, we can decide, and especially having those data on the density, thermal insulation of the material, and also the amount of humidity that the materials can absorb. Thanks to it, we're able to decide. So that's good. You can show it to these kind of things to us. One thing that you didn't speak about, and I don't know if you have been through it in your research, is because you propose that there can be different type of fibers that can be used. And then, of course, those walls are usually being plastered. And so the mechanical property are important, not only the compression, but if the plaster can stick enough to the wall, or if the wall is strong enough to receive any shocks. I don't know if you have made some comparison between the different type of fibers or the different type of earth about it.
Yeah, so no, I during the study I didn't do other types of fibers than hemp. I saw some studies of other people on flax sheaf and on sunflower barks, and it was working also. So the thing is, it does not that much depends on the types the type of fiber. I think maybe because they all are kind of mechanically resistant. Maybe the only one that can cause problems is the sunflower bark, because it's like I mean, it's really yeah, I mean, I don't know, but it's not that much resistant. But all the others, I don't think that can cause problem. But and on the type of earth, it's the same thing that I said before. It's you have to have a minimum amount of clay. What I saw is that actually all the mixes that I have been able to make that didn't crumble down during the making process was able actually to receive a plaster. So when I had like the kind of earth that was too sandy, then I didn't. I mean, the sample was I mean already crumbling down, so you cannot do anything with it. So yeah, you have to have the good amount of fine particles, and then you can do plaster with it.
And another question still about these mixes. What would be the thickness, the maximum thickness of wall you recommend to be able to dry? Because I mean, we are working on walls sometimes that are 30-35 centimeter thick, and but of course we don't know. We don't open them because it's directly on the building. So because of the climate, we are pretty sure it's drying. But do you have any maximum size? What do you think about it?
I don't actually. I'm sorry, but yeah, because I mean I'm not really. I mean, I have some example. I have some connection with people that are really building. I mean, these are their work, but what I saw is that yeah, maximum what was done, it was 35-40 centimeter, and but it was always done during the summer or just before, but never in winter, and not even like September, October. It was too late already, because like after during the winter it's not drying, and then and then it's not good for the material. I mean, I saw an example. I have like an example, that it's good to say. It's that I saw building sites in the countryside where they were spraying on the wall by the inside. And it was done late in the summer. It was like end of August, beginning of September, and 2 weeks after, we had like massive mushroom on the wall that were growing. So yeah, but the thing is that they put big ventilators inside. They opened the building completely, and it was I mean, the surface was dry like 2 weeks more after, so 1 month of drying, and they just kept the first centimeter, and then they could add the plaster, and it was good. So yeah, sometimes you can have this kind of problem, but they took some samples through the wall, and actually it was drying also through the wall, so no problem. But yeah, you have to be careful. I mean, you have to be careful to the period you implement it. You do the light earth so that it can dry. Yeah.
Okay. Thanks a lot. And I think you also have a question.
I have the opposite of this, the opposite question. The minimum thickness, because we have in Turkey several times we had and will have the situation that people are asking for a earthen plaster, but just because of decoration. They like the surface. Oh, it looks nice. So they don't care about the performance. it's not a problem for them, the performance. It's just a decoration. And it's a stupid situation, but it's real. So do you have any can you say about something about the minimum? So by these kind of questions, I always say don't use it for that kind of reason, but it's still the situation here.
I mean, I think it's not that that it just depends on the situation, like, because sometimes it's useful to do it. I mean, even a little thickness if you're on kind of cold region, cold climates, and you have like stone walls. Why? Because like the stone walls are quite cold at the sensation when you're around them, and the fact that you put like earth hemp render, it's making a surface that is warm at the sensation. So yeah, so even if you put like 2, 3, 4 centimeter on the stone wall, then they be able to warm less their interior and maybe consume less energy because they have less cold sensation on the inside. So yeah, sometimes actually we in France, when we have some renovation and people don't want like a big thickness, like 20 or 30 centimeter, we do 6, 7, and we applied it with a trowel like this, and actually it cuts the cold sensation of the wall.
So you reach a warm surface, and that's a very valuable argument. But yes, if it's only decoration, it makes no sense.
Yes, if it's only decoration.
That kind of arguments, they are very logical. Yes, thank you.
You're welcome.
But in your tests, when you reach the density and the performance, for example, on your curve, so which kind of thickness did you use for your tests in light earth? So you should ask the performance, density, and the insulation performance, for example. I think you used always one thickness, wall thickness.
So for the quantification of the conductivity, actually it's like normalized. What we do in the laboratory, it's 10 centimeter, what I did. But then the result is usable for any kind of thickness.
But for 10 centimeters, so you can reach the with the mostly fiber concentration, you can reach the very good performance.
Yeah. I mean, here I speak in thermal conductivity, but you can use also the thermal resistance. I don't know if you know, yeah, but so it's the thickness divided by the thermal conductivity, and so then it gives you really the thermal resistance in terms of thickness of your wall. So, but here, yeah, I give the results for any thickness.
Right. So the thermal conductivity is not dependent on the thickness. So that's the reason why it is done with 10 centimeter thick samples, but the result here is not depending on the thickness. So it could be done with 5 centimeter thick samples or 25. It wouldn't be the same results again.
Mm-hmm. Thank you.
Okay. I don't know if there is other question. I would have hundreds of questions, but time is passing, and I don't think we can. We should keep Theo longer, but if Theo, before leaving, you could show this large building with preparing a lot of panels. Just again, because seems very interesting to me to see that we can have that it is possible to build very large building with this kind of technique. So thanks a lot for sharing it. I didn't know that so large building were done already. So I'm really happy to see that it is possible. So
yeah, sure. So maybe just an anecdote on this one. Actually, it is very interesting, but it's a little bit specific because so ACTA, the society that is doing this, they use earth in bags. They buy earth that is already prepared. They don't do the earth lip themselves. So they have something that is already characterized and easier to maintain in time. They don't have variability during their building. So
okay.
But yeah, still it's impressive.
Okay, so then thanks a lot for all of this, Theo. And
Thank you.
It was really informative. And I guess you share your address. So if someone has any question, maybe they can contact you or anything. So thanks a lot again for it. And wish you a good evening. Thanks to everyone for attending to this event. And as soon as possible, we will have it with some Turkish subtitles.
Thank you very much.
Thank you everyone. And I hope I'm gonna be able to reach to you soon. See you.
Bye bye.
Bye.
Thank you. Bye bye.